Good morning to all. This is third lecture, and in this lecture, we will be covering maxima, minima topic. Okay. So here is the yeah. So it's an introduction in calculus, determining the just a minute. Yeah. So determining the local maxima and local minima of a function is essential for understanding its behavior. The first derivative test is a powerful method to identify these points by analyzing the sign changes of the derivative. So basically, we will be covering the problem based on maxima, minima, and there are methods to find out the maxima, minima, or in other words, extremum of a functions. So we'll be studying three methods. One is the using first derivative test. Second one is using the second derivative test for one variable we will do. Similarly, we'll do for the two variable. And then there is a Lagrange multiplier method that also we will see in this lecture. So how to find the extremum value using Lagrange multiplier. So for the one variable and with the first derivative test, our very first task is to find out the critical points. Now, how to define a critical point? This is also called as a stationary point also. So a critical point of a function fx is a point x equal to c in the domain of f where f dash c is equal to 0 or f dash c does not exist. But f of c is well defined, right? So these points are basically a potential candidate or potential location for local maxima, local minima, or saddle points or point of inflection. Now, what is a local maxima? So where the function reaches a peak, and local minima where the function reaches the thought, and saddle point or point of inflection where the function changes curvature but not necessary directions. So let's go with the first derivative test or first derivative principle. It says if f is continuous, so we assume that f is continuous. Moreover, it must be differentiable. And then if f dash x changes from positive to negative at x is equal to c, then f of c is called as a local maxima. And if f dash x changes from negative to positive, then f of c is called as a local minima. And if f dash x does not change sign at x is equal to c, then f of c is not a local extremum point. Okay, so now for doing the first type, that is first derivative principle, what are the steps involved in it? So first one is the compute the first derivative. Second one, find the critical point or stationary point. Third one is the create the sign chart of f dash x around each critical point, and then analyze the sign changes of f dash x to determine the nature of each critical point. So here this these 2 points are very important. If f dash x changes from positive to negative, then we call f at c is local maxima. If f dash x changes from negative to positive, then we call it as local minima. Okay, so graphical interpretation, if f dash x greater than 0, we say that function is increasing. I'm sure that everybody knows this. Everyone knows this. And similarly, if the derivative is strictly less than 0, then we call it as a decreasing function. So a change from increasing to decreasing indicates that the local maxima, right? So hence we said that here when f dash x changes from positive to negative, that is a change from positive to negative. So it means that it is local maxima. So basically the function is going this way graphically. So this point is local maxima. And similarly from positive to negative when it goes, so it is local minima in that neighborhood. Okay, changes from decreasing to increasing indicates a local minima. Okay, so here are the some problem. The problem number 1, that if f of x is equal to x cube minus 3x square plus 2, find the local maxima and minima using first derivative test. So we are going to basically go through with these steps. So these are the 4 steps that compute f dash x, find the critical point, then create a sign chart for f dash x around each critical point, and analyze the sign changes of f dash x to determine the nature of each critical point. So let's do this one by one. So what is f dash x here? So derivative of f with respect to x is x cube is 3x square minus 6x plus 0. So this is, let me take 3x common. So it is x minus 2. And now f dash x is equal to 0, we substitute. So f dash x is equal to 0. This would imply 3x times x minus 2 is equal to 0. This would imply x is equal to 0 or x is equal to 2. So critical point are basically here. Basically x is equal to 0 and x is equal to 2. These are two critical points. Now, as a stay, first compute the first derivative, then second derivative, then we have also calculated the second critical point. Now we'll analyze a sign chart. So now before 0, what is the nature of f dash x? Between 0 to 2, what is nature of f dash x? And after 2, what is nature of f dash x? That we will analyze here. So now here, what is my f dash x? So f dash x is equal to basically 3 times x minus 2, right? So this is going to be. So let's find out if x is strictly less than 0. So what happens to f dash x? So if x is less than 0, then you could see that here 3x will be negative, or x is negative, and x minus 2, if x is less than 0, then x minus 2 is positive or negative?
Overall quantity will be positive.
Overall quantity will be positive. That's true. This is negative. This is negative. Negative, negative. When you multiply, it will be positive. So f dash x is strictly greater than 0. It's very clear. So if x is less than 0, your f dash x will be greater than 0. Now, second, if x is between 0 to 2, so what will happen to f dash x? Let's analyze this.
It is
So this 3x is positive, greater than 0. What happened to this? X minus 2, it is positive or negative?
it is negative.
It is negative. So product of positive, negative. So it will be a conclusion will be, it will be less than 0. Is it okay?
Yes, sir.
Yeah. And the third type, that is when if x is strictly greater than 2, this would imply, so when x greater than 0, this is positive, this is positive. So resultant f dash x is also positive. So f dash x is strictly greater than 0. Now you could see that when x is less than 0, the function derivative is positive, and after 0, it is less than 0. So there is a change from positive to negative. So at x is equal to 0, f dash x changes sign from positive to negative. If there is a change from positive to negative, then we call f at, so x is equal to 0 is local maxima or local minima?
Local maxima.
Yeah, is local maxima. Right? Here we have already written that. If you can, so a changes from here. Yeah, f dash exchanges from positive to negative, then f at c is called a local maxima. F dash exchanges from negative to positive, then f at c is called local minima. And now from at 2, before 2 the f dash x is less than 0, and after 2 f dash x is greater than 0. So there is it changes from negative to positive, implies that at x is equal to 2, f dash x changes sign from negative to positive. Then in that case we call x is equal to 2 is local. What can I say? It is local.
Minima.
Very good. Okay, so the question was find the maxima, minima using the first derivative test. Of course, there are various methods. So I just wanted to show how the first derivative principle test is useful to find out the maxima, minima. One may get the similar conclusion with another method also. Right. So this here the problems completed. So here I have also given a solution f dash x, critical point 0 comma 2. These are the chart I have made, and then conclusion, local maxima, local minima. So on the similar line there is one more, find the local extrema means it's either minima or maxima. The point which is either maximum or minimum is called as the extremum point. So using the first derivative test, again there is another question. So let's find out f dash x here. So f dash x is equal to 4x cube minus 16x plus 0. This is same as, you can take 4x common, so it will be x square minus 4, and this is same as 4 times x. X square minus 4 can be written as x minus 2, x plus 2. So, so therefore your f dash x is basically 4x, x minus 2, x plus 2. So to get the critical point, that means when f dash x is equal to 0. So critical point we can easily identify. Critical points. So at what point f dash x is equal to 0? Basically at x is equal to 0, at x is equal to 2, and x is equal to minus 2. At those points f dash is 0. So critical points are x is equal to 0, x is equal to 2, and x is equal to minus 2. So you got a 3 critical points, that is 0, 2, and minus 2. These are the 3 critical points we got. So now next task is to, once you get a critical point, then observe the pattern of that derivatives. So first derivative. So here now we will analyze the following cases when x is strictly less than 0, when x between 0 to 2, when x between 2 to minus 2, and when x is strictly greater than minus 2. Okay, so here if x is strictly less than 0, let's understand what is f dash x. Can somebody tell me what is f dash x? I know that my f dash x is, what is my f dash x here? My f dash x is, I'm writing with a red pen so that you can easily check whether it is positive or negative, right? So this is my f dash x. So if x is strictly less than 0, can you tell me whether f dash x is positive or negative?
It will be positive.
It will be positive, clear? Maybe I should take 0, 2, minus 2. I should start with, I'm sorry. I should start it because in a real line minus 2 से start करूँगा, because This is 0, this is -2. Here it is 2. So I will cover first points which are below -2, then I will cover from -2 to 0, then I will cover points from 0 to 2, and then I will cover all the points after 2. So I should start with x is strictly less than 2, -2 first. Now you tell me, if x is strictly less than -2, what happened to f dash x, whether it is positive or negative?
It will be negative.
It will be negative because this is negative, this is less than 0, this will be less than 0 or greater than 0, x plus 2. This will be also less than 0, and this will be x plus 2. This will be also less than 0. Product of three negative number is negative, so this will be less than 0. Okay, now second case, we'll have to see from second part. If f is if x is between -2 to 0, let's analyze the derivative f dash x, whether it is positive or negative.
It will be positive.
It will be positive clearly, because you can see that when x is less than 0, this will be negative. X plus 2 will be greater than 0, and this will be again x plus 2 is a, yeah, what will be the x plus 2? X plus 2 will be positive. When x is less than 0, this will be less than 0. X minus 2. X minus 2 will be positive or negative?
So negative, I think so.
It will be, yeah, it will be negative, and this will be x plus
Positive.
2 will be positive. So resultant will be greater than 0. Very good. -2 to 0, it is positive. Now third case is if x lies between, what will be the third case? -2 to 0, then less than -2, -2 to 0, and now it is from 0 to 2. Let's analyze again what is my f dash x. Can you tell me now what is f dash x? Positive, negative? Now x is positive, here x is positive, so this is greater than 0. This x minus 2, so this will be less than 0. And I think x plus 2, this is again greater than 0. So positive, negative, positive. So ultimately it will be negative. And the last one is if x is strictly greater than 2, let's find out what is f dash x.
It will be positive.
It will be positive. Now you could see that from -2 to uh, uh, from at -2, it is negative and then positive. So derivative changes from f dash x changes from positive to negative. So that means what will be the x is equal to -2 is point of maxima or point of minima? Negative to positive. When there is a change of derivative from negative to positive, then that point is called as a point of, we have written here, if you see. If f dash x changes from positive to negative, then local maxima, and negative to positive, that means it is local minima. Now here, what happening? Negative to positive. I should have maybe here. From negative to positive. So what I can say? It is point of maxima or minima?
Local minima.
Yeah, local minima. Okay. Now x is equal to 0. At x is equal to 0, you could see that it is positive to negative. So then it is local maxima or minima here. X is
Maxima.
equal to 0 is maxima. Very good. Excellent. Now from at x is equal to 2, it is negative to positive. What is conclusion now? X is equal to
Minimum.
2 is very good. Local minimum. Right. So at last we got a conclusion. X is equal to -2 is local minima. X is equal to 0 is local maxima, and x is equal to 2 is local minima again. Right? So the same solution I have written here. So you could see that this chart, and I think let me cross check my conclusion. X is equal to -2, local minima, perfect. X is equal to 0, local maxima, and x is equal to 2, local minima. That's correct. Now we'll move towards the second derivative test. Of course, I'll give you the additional problems where you can apply the first derivative test and find out the local maxima or minima. Right. So we'll move to the second part of how to find out maxima minima using the second derivative test. So what second derivative test says, a point x is equal to c is a critical point. Yeah, that's the same. This we have already seen. Now second derivative test is this. So if f double dash c exists, and if it follows any one of this, then we conclude with the following. If f double dash c is greater than 0, then c is called as a local minima. And if f double dash c is strictly less than 0, then it is a point of local maxima. And if it is 0, then test is inconclusive, and such point is also called as a point of inflection. Right. Now the question is, find the local maxima and minima of the function f of x is equal to x cube minus 6x square plus 9x plus 1 using the second derivative test. So let's do this. So my f dash x is here. It is x cube minus 3x square. So it is 3x square minus 12x plus 9, which is same as, let me take 3 out. So it will be x square minus 4x plus 3. And now I can write down this as 3 times. Yeah, this can be written as x minus 3 and x minus 1. So my f dash x is equal to 3 times x minus 3, x minus 1. So now you can see that critical point we can easily write down. So critical points. So what are the critical points here? X is equal to. So basically you have to substitute f dash as 0, then you'll get a critical point. So here the critical point is x is equal to 3 and x is equal to 1. These are the two critical points we got. Right. So second derivative test says that once you calculate the single derivative, then you find out the first find out the critical points, then go for the second derivative. So now here f double dash x. Yeah. So this is my f dash x. So f double dash x is now from this I can find that f double dash x. It is 6x minus 12 plus 0. Basically 6x minus 12. Now let's find out critical point at x is equal to 3 and x is equal to f double dash at critical point 1 and 3, and we'll observe the nature of f double dash, and based on that we'll decide maxima minima. So when x is equal to what is f double dash at 1? F double dash at 1 will be 6 times 1 minus 12. So it is 6 minus 12. So which is minus 6 and which is less than 0. So what this would imply, I got f dash at 1, double dash at 1 is strictly less than 0. And when the double derivative is less than 0, then we say here, we have already written, when double derivative is strictly less than 0, then f has a local maxima at x is equal to c. Now here my conclusion is, therefore, f has local maxima at x is equal to 1. Now we'll find out, we'll check out for x is equal to 3 now. When x is equal to 3, let's find out what is f double dash at 3. F double dash at 3 will be here 6x minus 12. So 6 into 3 minus 12, 18 minus 12, which is 6, which is strictly greater than 0. So now I can say that, so this would imply f double dash at 3 strictly less than 0. Therefore, f has local, I have written, it should be positive, right? Because f double dash at 3 is 6, which is greater than 0. So therefore, f has local minima at x is equal to, and we may find out maxima value or minima value. So if somebody asks you what is maximum value of f, then you have to substitute x is equal to 3 in this. X is equal to 3. If you find out f at 3, you'll get local maximum. So a function local maximum value exact. Okay, so f has a local, maybe at 3 it is minima, no? So I put here local minima. And this max minima is is very useful in the economics. So arts people use it for means it has a lot of practical applications for the transportation problems, optimization theory and all. So here now we got a f as local minima at x is equal to 3. Maybe the problem is over here. Here you'll get a solution. F dash x we have calculated. So this x is equal to 1 comma 3 is a critical point. Then I have gone through the second derivative. Then less than 0 local maximum, greater than 0 local minimum, and here evaluate the value. So f at 1 is equal to 5, f at 3 is equal to 1. So maximum value is 5 and the minimum value is 1. So at last with the conclusion, local maximum at x is equal to 1, which is equal to 1. 5, f at 1 is 5, and local minimum at x is equal to 3, f of 3 is equal to 1. Right? Is it okay?
Yes, sir.
Okay. So we'll move ahead now. Now we'll go for the maxima and minima of functions of two variables. Right. So let f of x comma y be a function of two variables. Now how to find out maxima and minima for the two variable functions. So now here first thing is again a critical points, and the ideal there we had we calculated ordinary derivative. Now when you have more than one independent variable, you're supposed to go for the partial derivative. So now if I want to find out a critical point, then you basically find out, so x naught comma y naught is a critical point if the dou f by dou x at x naught comma y naught is equal to 0. And so basically you are finding the gradient of f, grad f, which is equal to dou f by dou x comma dou f by dou y, and you are replacing or you are substituting this gradient with a 0 vector. So now here it is 0 comma 0. You first find out the gradient, evaluate it at 0 comma 0, then you get x naught comma y naught, which is called as a critical point. And for the second derivative test, your Hessian matrix you need to find out. So what is Hessian matrix? So H is equal to basically dou 2f upon dou x, dou x square. It will be dou 2f upon dou 2x, then dou 2f upon dou x dou y, dou 2f upon dou y dou x, and dou 2f upon dou x dou x. Right. So now you find out the Hessian matrix at x naught comma y naught. So it's a determinant. So define the Hessian determinant. So it is basically determinant of it is basically a determinant of this matrix. So if the determinant D strictly greater than 0 and fxx is greater than 0, then it is called as a local minima, right? Fxx means dou 2 f upon dou x square. So this should be at x naught comma y naught. This should be greater than 0. And similarly, if d greater than 0 and fxx less than 0, then it is local maxima. And if it is less than 0, then it is a saddle point. And d equal to 0, the test is inconclusive. We'll go for the problem now. Find and classify the critical points of the function f of x comma y is equal to x cube plus y cube. So the first task is to find out the stationary point. So dou f by dou x here, that is 3x square minus 3y, then dou f by dou y, it is 3y square minus 3x. Okay, so what will be the double derivative now? Fxx will be 6x, make fyy is equal to 6y. So I'm sure that this is fx basically symbol, and this is fy. And what will be the fxy? So you either either differentiate fx with respect to y, because the mixed partial derivative are equal. The first partial derivative are continuous. So we are in this problem the fxy and fyx is always same. So now what is fxy? So if you now differentiate this fx with respect to y, you will get answer as -3. I think here I have made it as 2x. Similarly, you if you want, you can check fyx. So now fyx will be -3. So both are same. Now Hessian determinant, Hessian matrix H is equal to here 6x -3 -3 6y. And the determinant D is basically 36 times xy minus 9. Right. Maybe I have not calculated the critical points. So how will I calculate the critical point now here? Fx, you have to, fx is equal to 0. This would imply 3x square minus 3y is equal to 0. So this would imply x square is equal to y. And similarly, I'll substitute fy is equal to 0. So this would imply 3y square minus 3x is equal to 0. So this means y square is equal to x. So from this 2, if you substitute this 2, we'll get, okay. So here x is equal to, so x raised to 4, if you square to number 1, x raised to 4 is equal to y square, but y square is equal to x. So you got x raised to 4 is equal to x. So x raised to 4 minus x is equal to 0. And this can be easily solved. So it is, if you take x common, so x cube minus 1 is equal to 0. So of course this expression has 4 roots. One is x is equal to 0. This x cube minus 1 will have a cubic formula, a cube minus b cube formula you can apply. And here you could observe that one root is real, whereas another two roots are the complex. So one is and the complex root, whenever they occurs, they always occurs in a conjugacy. So here, and we are interested only in a real number, a real root. So here x is equal to 1 is another real root. So basically the expression or stationary point here, when x is equal to 0, x is equal to 1. These are the two values of x we got. So but when x is equal to 0, we'll have to find out what is y. Then y we have to find out. How to get y? You substitute any here, either x is equal to 0 or here you'll get the value of y. So when x is equal to 0, then y is also 0. And when x is equal to 1, then again you can resubstitute, you can substitute here or here, you get y is equal to 1. So now it is in R2. So the stationary points or critical points are in the ordered pair. So stationary points are here. Stationary points are basically 0, 0 and 1, 1. These are two stationary points. Right. Now we'll go for the Hessian determinant. So D is basically 36xy minus 9. So let me change the page so that. So now here D at 0, 0 will be minus 9, which is less than 0. So our conclusion says that if D is strictly less than 0, then this point is called as a saddle point. So here we conclude that 0, 0, 0, is saddle point. And second time we have to find out D at 1, 1. D at 1, 1 is 36. X is 1, y is 1. 36 minus 9, which is 27, which is greater than 0. So now D is greater than 0. In conclusion, D is greater than 0, D is greater than 0. Now we have to check the nomenclature, or maybe we have to check the what is fxx, the double derivative of f with respect to x at that point, whether it is positive. If it is greater than 0, then we say minima. If it is less than 0, we say it is maxima. So now what is fxx here? And fxx at 1, 1. So fxx we have already calculated, it is 6x. So it is 6. So which is greater than 0. So D is greater than 0. fxx is greater than 0. This would imply 1, 1 is point of, what is point of? Here we have written D greater than 0, fxx greater than 0, then it is a point, local minima point. Then it is point of minima. So in conclusion, 0, 0 is a saddle point and 1, 1 is a point of minima. That is what we got. Right. So here maybe you'll get a solution fx, fy, x square, y square. Then we got x is equal to 0, 0. So the critical points, double derivative. Then evaluate the Hessian determinant, that minus 9 saddle point, then 27 greater than 0. So local minimum. So in conclusion, 0, 0 is the saddle point, 1, 1 is the local minimum. Here is one more question quickly we'll take. Yeah, I have some, maybe what is fx? Fx is 2x plus 4, and we'll substitute the 0 again. So x is equal to minus 2 we will get fy, partial derivative of function with respect to y. It is 2y minus 6 is equal to 0. This would imply y is equal to 3. So this would imply minus 2 comma 3 is critical point. And now we go for fxx. So fxx will be, here it will be 2, fyy will be 2 again, and fxy, differentiate this with respect to y, this will be 0, so which is same as fyx also. So now your Hessian determinant H, matrix H will be, it is fxx, fxy, fyx, fyy. And the determinant, this would imply, you can find out determinant D as fxx, fyy minus fxy into fyx, but they are same only, so fxy whole square. So now you evaluate D at, so now here it is basically 2 into 2, 4, 4 minus 0, so it is 4. So you could see that D is constant, basically 4, which is greater than 0 at 2 comma minus 2 comma 3. And we can also find out fxx. Fxx, it is again a constant 2 greater than 0. So this would imply minus 2 comma 3 is local maxima, because D is greater than 0, fxx is greater than 0, then this point is called as a local maxima point. So first order derivative, this is just a detailed solution we have given. So fxx, fy, 0, 0. Yeah, it is 4. So I must have concluded. So yeah, the function has a local minima, and we have also calculated the minimum value of the function. Right. Now we'll move towards the Lagrange multiplier. That is, so is this okay? I just want to confirm from somebody. Are you with me? Yeah, participants.
Yes, sir.
Yeah, thank you so much. So to find extrema of f of x comma y subject to g of x comma y is equal to 0, use the method of Lagrange multiplier. The Lagrange multiplier is basically you have to, we are calling it as L of x comma y comma lambda. So you have to form this function f of x comma y minus lambda times g of x comma y. This lambda is called as a Lagrange multiplier. And then solve the system. So here you have a 3 variable. So x, y, and lambda. These are 3 unknowns we get. And to get the solution to these 3 unknowns, you find out dou L by dou x, dou L by dou y, and dou L by dou lambda. These 3 equations will give you the value of x, y, and lambda. And once we get x comma x, y, lambda, we'll substitute x comma y in a given function, and we'll get a maxima or minima of the respective function. Okay. So here is a question: maximize a product with a linear constraint. So here maximize the f of x comma y, which is equal to x comma y, and the constraint is given as x plus y. So now first task is we will write down this constraint in x plus y minus 10 is equal to 0, because we are constraint is always is, here we have g of x comma y is equal to 0. So my constraint is basically x plus y minus 10 is equal to 0. Now my Lagrange multiplier is Yeah, my Lagrange multiplier here is L is equal to, basically L will be a function of x, y and lambda here. Here it is x comma y comma lambda. So it is basically f of x comma y minus lambda times, this is my g, so g of x comma y, so which is equal to xy minus lambda times x plus y minus 10. Now you find out the derivative of lambda. This is L of x, y and lambda. Now find out the derivative of L with respect to x, y and lambda. So dou L by dou x will be uh, it will be y minus x, so it is lambda only, and substitute to 0 to get the critical point. Yeah, so then similarly dou L by dou y, it will be derivative of this will be x minus lambda, which is equal to 0, and the third part will be find out the derivative with respect to dou L by dou lambda, so that will be minus x plus y minus 10 is equal to 0. Now this will give you y is equal to lambda. This will also give you x is equal to lambda, and this will give you x plus y minus 10 is equal to 0. So in y is equal to lambda, x is equal to lambda, if you substitute here, you'll get 2 lambda is minus 10 is equal to 0, right? So this would implies that lambda is equal to 5. When lambda is equal to 5, you can easily get x and y because lambda, x and y are the same. So this would imply x is also 5 and y is also 5. So here we have to find out maximum value of f, but at which point it occurs. So at x comma y it occurs, and that point, if you substitute here, you'll get the maximum value of f of x comma y, satisfying this constraint x plus y is equal to 10. So therefore, f maximum value of f occurs at 5 comma 5, and that is equal to 5 into 5, because f of x comma y is x into y, so which is equal to 25. So maximum point is 5 comma 5 and the maximum value is 25. Yeah, so the same thing I have tried to answer here with the notes I'll definitely share with you all. So you can see that x plus y, and then here x is equal to y is equal to 5, so maximum value is 25. The another quick question, minimize distance to origin on a line. Now f of x comma y is equal to x square, here constant is x plus y. So you can see that the function L is basically x square plus y square minus lambda times x plus 2y minus 6, right? And now here I will find out partial derivative with respect to x, which is 2x minus lambda, which is equal to 0. Similarly, partial derivative with respect to y, 2y minus 2 lambda, that is 0. And derivative of L with respect to lambda will be minus of x plus 2y minus 6 is equal to 0. And this will give you basically lambda is equal to 2x. This will give you lambda is equal to y. And this will tell you that x plus 2y minus 6 is equal to 0. So if you substitute here x and y value, you'll get x is equal to basically lambda by 2. Y to y is basically 2 lambda, and this is equal to 6. This is basically lambda by 2 plus 2 lambda. This will be 5 lambda by 2 is equal to 6. So this would imply lambda is equal to 12 by 5. And if the lambda is cleared, you can easily get the x. So therefore, x is equal to lambda by 2, which is equal to 12 by 5 by 2, which is equal to 6 by 5. And y, what is y here? My y is lambda only, so it is 12 by 5. And then you can find out they have asked you to find out the minimum value. So minimum value is f of x comma y is equal to x square plus y square. So you just have to substitute this. I'm sure that here I have done it that. Yeah. So here, yeah, x is 6 by 5, y is 12 by 5, and then f evaluated at 6 by 5, 12 by 5, that will give you the answer as 7.2. Right. So with this, you can using with this constraint, we could find out the minimum distance to origin on a line. That is basically 7.2. So this is how the Lagrange multiplier. So of course here I have taken only one constraint. One may have more than one constraint. So in that case, how to solve? For example, now I may have a two constraint, g1 of x comma y is equal to 0. Similarly, g2 of x comma y is equal to 0. So in that case, you have to find out L will be basically your f minus lambda 1 times g1 minus lambda 2 times g2. So likewise, you can form the Lagrange multiplier and evaluate the respective, get the values of x, y, and lambda. And solving those three, you will get the required maximum value or minimum value. So this method is also one of the powerful method to find out the maxima or minima of a function. This is highly useful in the optimization techniques. So I think I have done from my side. If you have any doubt, you can ask. Otherwise, I'll stop.
Sir, if we have more than two constants, then
Yeah, I said, na, here if you have more than two constants, here, this one. So if you have a three constant, then you will have minus lambda 3 times g3 of x comma y.
okay, sir, fine.
Yeah. So that's it from my side. Maybe we have a next lecture, and in that next lecture, we'll try to cover the Riemann integrations, the problem based on the Riemann integration, and then we'll stop. Thank you so much. If you have any doubt, you can ask. I'll wait for another 10 to 15 seconds, and then we'll stop.
Participants, if there are any doubts, please ask.
Yeah, thank you, madam. Thank you so much. Yeah.
Thank you, sir. Tomorrow, same time, we'll meet for the last session. Thank you very much.
Yeah. Thank you.